Matter is lying to you. Every surface you have ever touched, every wall you have ever leaned against, every floor that has ever held your weight, all of it is almost entirely nothing. Not mostly empty, not roughly hollow, but overwhelmingly catastrophically vacant. The atoms that compose your body, the chair beneath you, the planet spinning beneath that chair, they are structured around a kind of engineered emptiness so vast that if you could somehow compress all the actual matter in every human being who has ever lived into a single object, removing every gap, every hollow, every quantum whisper of space between particles, the result would fit comfortably inside a sugar cube. A single sugar cube. That is the density of what we actually are beneath all the theater of solidity. And yet, here you sit, solid, reading, breathing, existing. The atoms in your fingertips are not touching the atoms in this screen. What you feel as solid contact is in fact a quantum storm of repulsion, playing out at distances so small they make a grain of sand look like a continent. You are, in the most literal physical sense, a ghost who has learned to push back. But there is a question buried inside this astonishing fact, a question that nearly broke physics when it was first properly understood. A question so dangerous to classical science that its answer required dismantling 2 centuries of intellectual certainty and replacing them with something so strange, so alien to ordinary intuition, that many of the physicists who built the new framework spent the rest of their lives uncomfortable with what they had created. The question is this: why is matter here at all? If you like this kind of deep exploration, a like and a subscribe would mean a lot to us. It genuinely helps more people find their way to these ideas, not in the philosophical sense, not the grand cosmic why that keeps theologians busy. The specific, technical, brutally concrete physical question: given that the electron carries negative charge and the nucleus carries positive charge, and given that opposite charges attract with a force that becomes stronger the closer they get, why hasn't every electron and every atom in the universe already crashed into its nucleus? The mathematics of classical physics says it should have happened in less than a billionth of a second after atoms first formed. Every atom, everywhere, all at once. A universe of collapsed matter, leaving behind nothing but radiation and silence. Instead, we have galaxies, we have oceans, we have roses and thunderstorms, and the human brain, which is itself an atom-built machine generating the very question that threatens to explain away its own existence. Something intervened, something in the deep grammar of reality inserted a rule that the classical world did not know about. A rule that says the electron stops, that it finds a floor, that no matter how powerfully the nucleus pulls, there is a level below which descent is simply not permitted. That rule is quantum mechanics. And the story of how physicists discovered it is one of the most dramatic intellectual journeys in human history. To understand why the electron refuses to fall, you first have to understand what the world looked like before anyone suspected it might refuse. At the turn of the 20th century, physics was in a state of magnificent confidence. James Clerk Maxwell had unified electricity and magnetism into a single elegant framework in the 1860s, producing 4 equations that seemed to describe everything electromagnetic with breathtaking completeness. Isaac Newton's mechanics, refined and extended over 2 centuries, handled the motion of everything from cannonballs to planets with almost supernatural accuracy. Light had been decisively shown to be a wave. Atoms, though still somewhat speculative, were increasingly accepted as real. The universe seemed to be, at bottom, a vast clockwork, deterministic, continuous, in principle completely predictable. There were loose ends, yes, a few stubborn experimental results that didn't quite fit. Most physicists assumed these were minor technical problems, the kind of thing that a clever graduate student would iron out in a few years. Lord Kelvin, one of the giants of 19th century physics, reportedly described the situation as a cloudless sky, with only 2 small clouds on the horizon. He was almost unimaginably wrong about the size of the clouds. One of those clouds was the problem of what happened when you heated an object and measured the light it emitted. Classical physics, when applied to this question, produced a prediction so spectacularly wrong, it became known as the ultraviolet catastrophe. The theory said that a hot object should emit infinite energy at high frequencies. Not a lot of energy, infinite energy. Every warm object in the universe should be pouring out bottomless reservoirs of high-frequency radiation. The fact that a glowing coal in your fireplace does not instantly vaporize the surrounding universe was, according to classical physics, simply inexplicable. The other cloud was the atom itself, and it was about to become a thunderstorm. In 1897, the British physicist J.J. Thomson was working with cathode ray tubes, sealed glass vessels from which most of the air had been pumped out, with metal electrodes at each end. Apply a high voltage and something flows through the vacuum, producing a faint luminous glow. Thomson already knew this radiation bent in electric and magnetic fields. By measuring that bending with meticulous care, he was able to determine something extraordinary. The cathode rays were not waves or exotic radiation. They were particles. Tiny, impossibly light particles, each one carrying a fixed negative electric charge. The mass of each particle was less than 1,000th the mass of the lightest known atom. Thomson had discovered the electron, and by doing so, he had proven that atoms were not the indivisible, featureless spheres that chemists had long imagined. Atoms contained something smaller. They had internal structure. The question was, what structure? Thomson proposed a model. Since atoms were electrically neutral overall, and since he had found that they contained negatively charged electrons, there had to be positive charge somewhere too. He imagined the atom as a sphere of diffuse positive charge, something like a cloud or a fluid, with the electrons embedded inside it, like fruit suspended in a gelatin mold. The electrons would sit at equilibrium positions, held in place by the balance of electric forces from the surrounding positive medium. It was a tidy picture, reasonable, consistent with what was known, and its central implication was that the atom was stable because the electrons had nowhere dangerous to go. They just floated in place, nestled in a cushion of positive charge. What killed this model was one of the most unexpected experimental results in the history of science. Ernest Rutherford was a New Zealander who had come to work in England with a reputation for creative and relentless experimentation. In 1909, working with Hans Geiger and a young undergraduate named Ernest Marsden, he set up an experiment that seemed almost trivially simple. He aimed a beam of alpha particles, the kind emitted by radioactive materials, each one consisting of 2 protons and 2 neutrons, relatively massive and fast, at an extremely thin sheet of gold foil. Then he waited to see where the particles landed on a detecting screen placed around the foil. If Thomson's model was right, the positive charge in the gold atoms was spread so diffusely that the alpha particles should barely notice it. They would sail through the foil like bullets through a fog bank, deflecting only slightly, producing a gently smeared pattern on the screen. Rutherford expected this. He designed the experiment largely to confirm it, to test the model's predictions with real data. Marsden set up a detector to look for any particles that might scatter backward, which everyone assumed would detect essentially nothing. It was a control measurement, an afterthought. What Marsden saw made him rush to find Rutherford immediately. Particles were bouncing backward, not many of them, roughly 1 in 8,000. But some were rebounding almost directly the way they had come, as if they had struck something solid, as if they had hit a wall. Rutherford was not a man given to theatrical exaggeration, but he later said that the result was as astonishing as if you fired artillery shells at tissue paper and they came back and hit you. The entire conceptual framework of the Thomson model could not produce this result. A diffuse sphere of charge cannot deflect a fast, massive alpha particle backward. You cannot bounce a bowling ball off of smoke. The only explanation was that the positive charge was not diffuse at all. It was concentrated, packed into a volume almost incomprehensibly smaller than the atom itself. Rutherford called this concentration the nucleus. He worked out its approximate size by analyzing the scattering angles. The nucleus was roughly 10,000 to 100,000 times smaller than the atom surrounding it. Picture a cathedral and place a single grape at the very center of the nave. That grape is the nucleus. The cathedral walls, far away in every direction, are where the electrons live. Everything between the grape and the walls is empty space. This picture of the atom, a dense positive nucleus surrounded at enormous relative distance by lightweight negative electrons, was beautiful and intuitive. It looked like a solar system in miniature, and it was, as a model of atomic structure, immediately and completely fatal. Not because the picture was ugly or implausible, because of what Maxwell's equations said about it. Here is the problem. The orbiting electron is an accelerating charged particle. Even if it moves at constant speed, an orbit requires constant change of direction. Change of direction is acceleration. And Maxwell's equations, the same equations that correctly describe every electromagnetic phenomenon, from the light of the sun to the signal in a radio antenna, say something absolute and non-negotiable about accelerating charged particles. They radiate energy. Not sometimes, not under special circumstances, always. Every accelerating charge emits electromagnetic radiation continuously. It is not a tendency or a preference. It is a mathematical consequence of the field equations that had been tested against every available experiment and never once failed. So, the orbiting electron would radiate. It would pour energy out into the surrounding space as electromagnetic waves, and as it lost energy, it would slow down. As it slowed, the electrical pull from the nucleus would tighten its orbit. A tighter orbit at the same charge means a stronger attractive force, which means faster orbital speed, which means more acceleration, which means more radiation, which means more energy loss, which means a tighter orbit still. The spiral accelerates as it progresses. Each step downward makes the next step faster. Physicists of the era calculated how long this would take for a hydrogen atom. The simplest possible case, a single proton and a single electron. The answer was roughly 10 picoseconds, 10 trillionths of a second. In that eye blink of time, the electron would complete its death spiral and slam into the nucleus. Not just for hydrogen, for every element. Every atom in the universe should have collapsed almost the instant it formed. Matter, as a stable, enduring phenomenon, should be physically impossible. And yet, the ground is solid. The stars have been burning for billions of years. You are reading these words. Classical physics was not approximately wrong about atomic stability. It was categorically, devastatingly, entirely wrong. The gap between what the theory predicted, atomic collapse in a trillionth of a second, and what observation showed, atoms lasting essentially forever, was not a rounding error. It was a difference of around 27 orders of magnitude. No tweaking of parameters, no refinement of the classical picture, no clever addition to the existing framework could bridge a chasm of that size. Something was missing at the foundational level. Some principle of reality that classical physics knew nothing about was operating inside the atom, preventing the catastrophe. Around this same time, another puzzle was demanding attention, one that seemed unrelated but would turn out to be deeply connected. When you heat a gas of hydrogen to high temperatures until it glows and then pass that light through a prism to spread it into its component wavelengths, you do not get a rainbow. You get something far stranger. A small number of isolated, brilliant lines of color against a background of absolute darkness. Not a smooth continuum of every wavelength, not even a broad smear, but precise, razor-thin lines appearing only at specific wavelengths, as if the hydrogen had a short list of allowed colors it was permitted to emit and refused to produce anything else. Other elements produce their own unique patterns of lines, each as precise and characteristic as a fingerprint. A Swiss mathematics teacher named Johann Balmer, working in 1885 with nothing but the published wavelength measurements and a talent for finding numerical patterns, discovered that the wavelengths of hydrogen's visible lines could all be generated by a startlingly simple formula involving whole numbers, just integers. The wavelengths were not arbitrary. They were governed by a relationship involving the simplest mathematical objects that exist. A Swedish physicist named Johannes Rydberg extended this formula to cover all of hydrogen's spectral lines, including those in the invisible ultraviolet and infrared. Again, whole numbers. Always whole numbers. No one knew why. If an electron could orbit at any distance and gradually spiral inward, it should radiate a continuous smear of all wavelengths as it descended. Discrete spectral lines implied that only specific transitions were possible. Only specific energy changes. That implied that only specific energies existed inside the atom. That implied that energy inside an atom was not continuous but came in discrete packages. And discrete packages of energy had a name by 1905, quanta. The first person to take atomic quantization seriously and build a working model around it was the Danish physicist Niels Bohr, who in 1913 proposed something that was scientifically scandalous and experimentally triumphant in almost equal measure. Bohr kept Rutherford's nucleus at the center. He kept the electrons orbiting it, but he declared, by pure postulate, that only certain specific orbits were permitted. Between those orbits, nothing, no intermediate distances, no gradual spiral. An electron either occupied one of the allowed orbits or it did not exist in between. And crucially, though this directly contradicted Maxwell's equations, he declared that an electron in one of these permitted orbits did not radiate. It simply moved without losing energy. The laws of electromagnetism simply did not apply at the atomic scale, Bohr asserted, in a way that clearly scandalized him even as he wrote it. To determine which orbits were allowed, Bohr reached for the constant that Max Planck had introduced in 1900 to solve the blackbody radiation problem. Planck's constant, an extraordinarily tiny number, approximately 6.6 to 6 times 10 to the minus 34 joule seconds, represented the fundamental quantum of action, the smallest possible unit of a quantity that had never previously been thought to be quantized. Bohr required the angular momentum of the electron to be a whole number multiple of this constant divided by twice pi. First orbit, 1 unit, second orbit, 2 units, third, 3, nothing between. From this constraint, he calculated the energy of each allowed orbit. When an electron jumped from a higher orbit to a lower one, it emitted a photon whose energy equaled the difference between the two orbit energies. Since only specific orbit energies existed, only specific energy differences existed, and therefore only specific photon energies, only specific wavelengths were emitted. Bohr worked out the mathematics and compared the predicted wavelengths to Balmer's formula and Rydberg's measurements. The agreement was exact. Every spectral line of hydrogen fell precisely where Bohr's calculation said it should. The whole numbers in Balmer's formula turned out to correspond directly to the whole number labels of the electron's allowed orbits. The empirical pattern that had puzzled spectroscopists for 3 decades was a direct window into the discrete energy structure of the atom. For the first time, someone had derived the spectral lines of hydrogen from a physical theory rather than guessing a formula from the data, and Bohr's model answered the stability question, at least partially. The lowest allowed orbit, the one labeled with the number 1, later called the ground state, had a specific finite radius, now known as the Bohr radius, approximately 53 trillionths of a meter. Below this orbit, Bohr simply declared, no orbit exists. The electron cannot spiral any closer because there is no closer orbit to spiral into. The model has a floor built into it by definition. But this answer was deeply unsatisfying because it was unexplained. Bohr could tell you where the floor was. He could not tell you why there was a floor at all. His rules worked, but they floated in midair, unconnected to any deeper principle. Why should electrons be forbidden from orbiting at intermediate distances? What enforced the quantization? What mechanism prevented the electron from choosing an energy between the allowed levels? The model offered no answer to any of these questions. It was correct in its predictions and silent about its reasons. The deeper answer would require an entirely new conception of what matter is. In 1924, a young French physicist completing his doctoral thesis proposed something that seemed almost too audacious to take seriously. That matter, actual physical matter, might have a wave nature, just as light did. Louis de Broglie had been thinking about the strange dual character of light, which had been decisively shown to behave like a wave in diffraction and interference experiments, but which also clearly behaved like a stream of particles in the photoelectric effect. Light, in some sense that nobody fully understood, was both. De Broglie's question was simple and explosive. If waves can behave like particles, can particles behave like waves? He worked out a relationship. Every particle, he proposed, has an associated wavelength. This wavelength is not arbitrary. It is determined by the particle's momentum. Larger momentum means shorter wavelength. For everyday objects, baseballs, people, cars, the de Broglie wavelength is so fantastically small that no conceivable experiment could detect it. The wave nature is there in principle and invisible in practice. But for the electron, which has such a tiny mass, the de Broglie wavelength at typical atomic energies is comparable to the size of the atom itself. For the electron, the wave nature is not negligible, it is everything. This was not treated as certain truth immediately. It was a hypothesis, elegant, surprising, and in need of experimental confirmation. The confirmation came 3 years later when Clinton Davison and Lester Germer, working at Bell Telephone Laboratories in New York, fired electrons at a nickel crystal and found, to their initial confusion, that the electrons bounced off in patterns that made no sense if electrons were particles. The patterns made perfect sense if electrons were waves. The electrons were diffracting, spreading out around the regular rows of atoms in the crystal lattice and interfering with themselves, creating regions of high and low intensity, exactly as predicted by de Broglie's formula. The same experiment George Thomson performed independently in Britain confirmed the result. Electrons were waves, real waves, not metaphorical ones. The evidence was unambiguous. And suddenly Bohr's mysterious quantization made sense, not as an arbitrary rule imposed from outside, but as a consequence of the electron's wave nature. Think about what happens when a wave wraps around in a circle. If the circumference of the circle is exactly one wavelength, the wave connects smoothly with itself, and you get a stable, self-consistent pattern, a standing wave, a wave that seems to vibrate in place rather than travel. If the circumference is exactly 2 wavelengths, you get a different stable standing wave. 3 wavelengths, another. But if the circumference is 1.5 wavelengths or 2 1/3, the wave returning to its starting point is slightly out of phase with itself. The crests don't align with the crests. The wave destructively interferes with itself and cancels out. It cannot exist. Bohr's allowed orbits were simply the orbits where the electron's de Broglie wave could form a stable standing pattern, where an integer number of wavelengths fit exactly around the circumference. The intermediate orbits that Bohr had forbidden were the circumferences where no standing wave was possible, where the electron's wave nature would tear it apart through self-interference. The quantization was not arbitrary, it was the mathematics of waves in confined spaces. But this picture, the electron as a wave rippling neatly around the nucleus in a circular standing pattern, was still too simple, too classical in its bones. It still imagined the electron following a path, tracing a trajectory, existing at specific locations. The full truth was stranger and more complete. It was articulated in 1926 by an Austrian physicist named Erwin Schrödinger, working in a concentrated burst of creative energy in a Swiss mountain retreat over Christmas, reportedly in the company of an unnamed lover whose identity historians have never fully established. Whatever his exact circumstances, the equations he produced over that holiday would change the world. Schrödinger wrote down a wave equation, now carrying his name as naturally as Maxwell's equations carry his, that described not the path of the electron, but something more abstract and more fundamental, a mathematical function assigned to every point in space, varying in time, called the wave function, and typically represented by the Greek letter psi. The Schrödinger equation tells you how this wave function evolves. Given the forces acting on a particle, the equation specifies precisely how the wave function changes, moment by moment, everywhere in space simultaneously. For a hydrogen atom, the relevant force is the electrical attraction between the proton and the electron, which gets stronger as the distance between them decreases, following Coulomb's law with perfect regularity. Plug this force into Schrödinger's equation and solve. What emerges, and this is the stunning part, is not a continuous range of solutions. The equation has solutions only for certain specific energies. Try to find a solution for an energy between 2 of the allowed values and the mathematics collapses. The wave function becomes undefined, infinite, or wildly oscillating in a way that has no physical meaning. Only at specific energies does the wave function behave properly, finite everywhere, smoothly varying, approaching zero at large distances, well behaved at the nucleus. These allowed energies are the energy levels of the atom, and they match both Bohr's postulated orbits and the measured spectral lines. The quantization is not put in by hand. It is not declared by fiat the way Bohr declared it. It emerges from the mathematics with the same inevitability that only certain wavelengths can fit between the fixed ends of a guitar string. The guitar string cannot vibrate at just any frequency because the wave must form a node at each fixed end. It must be zero there. This boundary condition selects the allowed frequencies automatically. The hydrogen atom cannot support an electron at just any energy because the wave function must behave properly everywhere. It must be finite at the nucleus and vanish at large distances. These boundary conditions select the allowed energies automatically. Quantization is not added to the physics. It is what physics in confined spaces does. But the wave function by itself is just a mathematical object. What does it mean physically? What is waving? Where is the electron? This question tormented the founders of quantum mechanics, and the answer that emerged, proposed by Max Born in 1926, was something that no physicist had anticipated, and that many, including Albert Einstein, never fully made peace with. The wave function does not tell you where the electron is. It tells you, at each point in space, the probability of finding the electron there if you look. More precisely, the square of the wave function's magnitude at any point gives the probability density, the likelihood per unit volume of detecting the electron in that neighborhood. The electron, before you measure it, does not have a position. It is not hiding at some definite location that you simply don't know. It is genuinely not anywhere specific. It is smeared across space in a probability cloud whose shape is given by the wave function. When you make a measurement, when you fire a photon at the atom and see where the electron is, the act of measurement forces the electron to choose a location, drawn from the probability distribution that the wave function describes. The wave function does not reveal a pre-existing fact. The measurement creates the fact. For hydrogen's ground state, the lowest allowed energy level, the wave function is a smooth, spherically symmetric shape that decreases exponentially with distance from the nucleus. The probability density is highest right at the nucleus. This seems alarming. It suggests the electron is most likely to be found right at the center, right inside the proton, which would seem to imply that the atom has already collapsed. But this inference forgets geometry. Probability density is probability per unit volume. Volume near the nucleus is scarce. The set of all points exactly one radius from the center forms a spherical shell, and that shell's volume grows as the square of the radius. Very close to the nucleus, even though the probability density is high, the available volume is so tiny that the actual probability of finding the electron there is small. The most likely location for the electron, integrating over the available shell volumes, turns out to be at a distance matching exactly the Bohr radius. The electron is most probably found precisely where Bohr's model said its circular orbit would be, but without any orbit, without any trajectory, without any path. The probability cloud is the electron, not a description of where the electron might be, the electron itself. Now we arrive at the heart of the matter. Now the answer to our original question becomes visible, rising out of the mathematical landscape of quantum mechanics like a mountain emerging from morning fog. Why doesn't the electron fall into the nucleus? The answer is the Heisenberg uncertainty principle, and it is one of the most consequential facts in all of physics. Werner Heisenberg, working in 1927, proved something that initially seemed like it might be a limitation of our measurement tools, but turned out to be a fundamental feature of reality itself. There are pairs of physical properties that cannot simultaneously have well-defined values. The most important pair for our purposes is position and momentum. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a specific value. Planck's constant divided by 4 times pi. This is not a statement about the limitations of our instruments. It is not a statement about our ignorance. It is a statement about nature. The universe does not contain the information required to give a particle a perfectly defined position and a perfectly defined momentum at the same time. The uncertainty is real. It belongs to the particle, not to us. Now watch what this does to any attempt to confine the electron at the nucleus. Confine the electron to a smaller region of space, which is what falling toward the nucleus would mean. And you reduce its position uncertainty. You know more precisely where it is because you have squeezed it into a smaller box. But the uncertainty principle says that reducing position uncertainty must increase momentum uncertainty. The electron's momentum becomes wildly indeterminate. It could be anything. It could be enormous. And momentum, particularly its square, is directly related to kinetic energy, the energy of motion. A large uncertainty in momentum means a large average kinetic energy. The tighter you squeeze the electron's position, the faster, on average, it must be moving. This creates a direct competition inside the atom. The electrical attraction between the electron and the nucleus pulls the electron inward. Getting closer reduces what physicists call potential energy, the energy stored in the separation between the two charges. Reducing potential energy is energetically favorable in isolation. It would seem to push the system toward collapse. But closing the distance simultaneously tightens the confinement, and tighter confinement means, through the uncertainty principle, larger average kinetic energy. Kinetic energy always contributes positively to the total. It cannot be reduced by confining. Confining increases it. So, you have two competing tendencies. The potential energy wants to pull the electron to the center, making it more negative as distance decreases. The kinetic energy, forced upward by the uncertainty principle as position uncertainty shrinks, pushes back. These two tendencies cancel at a specific distance, the point where the total energy, kinetic plus potential, reaches its minimum. This minimum energy configuration is the ground state. It is the floor. It is as low as the atom can go. Crucially, this floor is not zero. The ground state of hydrogen has an energy of approximately negative 13.6 electron volts. Negative because the electron is bound. It takes energy to remove it, but not infinitely negative, not zero. The ground state sits at a specific finite non-zero energy, and this finite energy corresponds to a specific finite non-zero spatial extent. The electron is not at the nucleus. It is in a probability cloud spread around the nucleus, with its most likely position at the Bohr radius. What would happen if you tried to push the electron all the way to the nucleus, to localize it in a zero volume point at the center? The position uncertainty would collapse towards zero. The uncertainty principle would then demand that the momentum uncertainty blow up toward infinity. The kinetic energy would become infinite. A state with the electron perfectly localized at the nucleus would be an infinitely high energy state, not a low energy state at all. It would be the opposite of stable. Nature, always seeking the lowest available energy, recoils from it automatically. The electron does not fall into the nucleus because falling to the nucleus would require climbing to infinite energy. The quantum structure of reality makes the nucleus unreachable, not by pushing the electron away, but by making the journey itself energetically catastrophic. There is no force holding the electron up. There is no barrier it must overcome to fall in. There is simply nowhere to fall to. The ground state is the bottom of the ladder, and the next rung down does not exist. Energy is quantized in the atom, and the lowest quantum of energy available corresponds to the electron being spread out in its probability cloud, not collapsed to a point. Below this state, there is nothing. Not a lower energy state, not a closer orbit, not a deeper configuration. The universe ran out of downstairs. This answer has a quality that no classical explanation could ever have. In classical physics, the stability of orbiting systems, planets around stars for instance, is contingent. It depends on the planet having exactly the right velocity to maintain its orbit. Too slow, it falls inward. Too fast, it escapes. The stability is conditional, forever balanced on a knife edge. Perturb it enough, and it changes. In quantum mechanics, atomic stability is absolute. The ground state does not depend on conditions. It does not require careful balancing. It is the mathematical floor of the system, mandated by the Schrödinger equation and the uncertainty principle together. You can heat the atom, cool it, shake it, irradiate it with light. Any of these can excite the electron to a higher energy level, but the electron will promptly emit a photon and return to the ground state. It always comes back. The ground state is not an orbit the electron might fall out of. It is where reality places electrons by default when nothing is actively exciting them. The spectral lines that puzzled spectroscopists for decades, the lines that Balmer described with his empirical formula and Bohr explained with his postulates, these emerge from transitions between discrete energy levels. When an electron absorbs a photon with exactly the right energy to jump from the ground state to the second level, it does so. When it spontaneously falls back, it emits a photon with that exact energy. The energy determines the frequency. The frequency determines the color. Specific energies produce specific colors and no others. The hydrogen spectrum is a direct readout of the atom's energy ladder, a portrait of quantum structure painted in light. But this is still not the deepest part of the story. We have explained why the electron stays where it is. We have not yet asked what the electron actually is, not where it lives or how it behaves, what it is. Every electron ever measured or observed has the same mass. Every electron has the same electric charge. Every electron has the same intrinsic angular momentum, a property called spin, that is fixed at 1/2 unit no matter what. These properties are not approximate. They are not statistical averages. Every single electron, and there are something like 10 to the 80th of them in the observable universe, is precisely identically, with no detectable variation whatsoever, the same as every other electron in existence. In the classical world, this would be baffling. If electrons were little physical balls, tiny specks of matter, then each one would be manufactured separately, and no manufacturing process produces identical objects at any scale. Coins stamped from the same die differ slightly. Atoms of the same element differ in their quantum states, their vibrations, their histories. The idea that you could produce 10 to the 80th separate physical objects and have them all be truly, measurably, structurally identical down to the last decimal place is not just unlikely. It is inconceivable. So electrons cannot be little balls of matter. They must be something else. And the theory that explains what they are is quantum field theory, specifically the portion dealing with electrons and photons called quantum electrodynamics, or QED. In quantum field theory, the fundamental constituents of reality are not particles. They are fields. A field is a physical entity that has a value, or a set of values, at every single point in space and at every moment in time. You are already familiar with fields in the classical sense: the temperature field in a room, the gravitational field of the Earth, the electric field surrounding a charged object. These are quantities that vary smoothly across space and time, with a value at each point. Quantum fields are similar in concept, but different in a deep way. They are quantum mechanical objects, subject to all the indeterminacy and quantization that quantum mechanics implies. They fluctuate. They have ground states. They respond to measurements in the quantum mechanical way. There is a field for every type of fundamental particle. There is an electron field that stretches across the entire observable universe, every point in space, every corner of every galaxy, the interior of every black hole, the void between superclusters. The electron field is everywhere, all the time, even in what we call empty space. And what we call an electron is a disturbance in this field, a localized excitation, a ripple, a vibration in the quantum medium. Imagine a still pond on a windless morning, its surface perfectly smooth. Now, a stone drops. Ripples spread outward, carrying energy and momentum, expanding through the medium, eventually dissipating. The ripple is not separate from the water. It is the water doing something. It is a pattern of motion in the underlying medium, localized for a time, possessing properties like energy and direction of travel, but fundamentally a feature of the field rather than an object that exists independently of it. An electron is like that ripple. When we say we have created an electron in a particle accelerator, what we mean is that we have added a quantum of excitation to the electron field. When an electron and its antimatter counterpart, a positron, which is an excitation of the same field but with opposite charge, collide and annihilate, those excitations disappear, and their energy flows into the electromagnetic field, manifesting as photons. Fields get excited, fields de-excite. What we call particles are the localized, quantized excitations that these processes produce and destroy. Now the identical nature of all electrons becomes obvious. Every electron is an excitation of the same electron field. Their properties, mass, charge, spin, are properties of the field itself, not of individual particles separately manufactured. Asking why all electrons are identical is asking why all ripples in the same pond are made of water. The answer is, because they are all expressions of the same underlying thing. The identity is not a coincidence. It is a structural necessity. Electrons are identical for the same reason that the letter A, printed 1,000,000 times by the same font, is always the letter A. They are instantiations of the same pattern, the same template, the same field. There is only one electron field in the universe, and all electrons are its ripples. This also illuminates why electrons appear, to all experimental investigation, to have no size and no internal structure. A ripple in a pond has a location and a wavelength and an energy, but it does not have components. You cannot open up a ripple and find smaller ripples inside it. The ripple is a pattern in the medium, and the medium has no internal compartments at the scale of the ripple. Similarly, the electron as an excitation of the electron field has properties, mass, charge, spin, that emerge from the mathematics of the field, but no subcomponents, no internal architecture. When physicists have collided electrons with other electrons, with positrons, with photons, at the highest energies available at every accelerator ever built, they find no sign of internal structure. The Large Electron-Positron Collider at CERN probed the electron down to distances around 10 to the minus 18 meters, 1 billion times smaller than a proton, and found nothing but a point particle. More recent experiments have pushed further still, with the same result. The electron is not hiding its parts. It does not have parts. It is fundamental in the same way that a question can be fundamental. It is not built from simpler questions. It is itself the primitive, the irreducible, the thing everything else is built from. But the electron, even as a fundamental excitation of its field, is never alone. It exists in constant interaction with the electromagnetic field, and this interaction is stranger and richer than any classical interaction could be. In quantum electrodynamics, the electron continuously emits and reabsorbs virtual photons. Excitations of the electromagnetic field that bubble up from the quantum vacuum briefly carry momentum or energy and dissolve back before they can be directly detected. These are not fully real photons in the ordinary sense. They are quantum fluctuations, transient disturbances in the field that arise because the uncertainty principle applies to fields just as it applies to particles. You cannot specify the exact value of a field and its rate of change simultaneously. Fields must fluctuate. Even in what we call empty space, the fields are not still. They churn and boil with quantum activity. This activity has measurable consequences. One of the most precisely verified predictions in the entire history of science involves what happens to the electron's magnetic properties when you account for these quantum vacuum effects. The electron, by virtue of its spin, behaves like a tiny magnet. The strength of this magnetic behavior is characterized by a number called the G factor. A naive application of quantum mechanics predicts the G factor should be exactly 2. But when you carefully include all the ways the electron interacts with the quantum vacuum, all the virtual photons, the fleeting electron-positron pairs that pop in and out of existence, the higher-order fluctuations involving virtual muons and quarks, you get a tiny correction to this value. The theoretical prediction from quantum electrodynamics, computed through staggering calculations involving thousands of Feynman diagrams, expanded to extremely high orders of precision, gives a specific numerical value for the electron's G factor that differs from 2 by about 1 part in 1,000. The experimental measurement, made using exquisitely sensitive instruments called penning traps that can hold a single electron in isolation for months while probing its magnetic properties, agrees with the theoretical prediction to roughly 11 significant figures. 11. In a science where agreement to 2 significant figures is often considered excellent and 4 is remarkable, agreement to 11 is essentially supernatural. It is the most precisely confirmed prediction of any theory in the history of science. This agreement is not just impressive numerically. It tells us something deep. QED treats the electron as a point particle with no internal structure, surrounded by its cloud of quantum vacuum interactions. If the electron were composite, if it were made of smaller constituents bound together at some scale, those constituents would alter its magnetic properties in ways that the QED prediction does not account for, and the agreement with experiment would break down. The fact that the agreement holds to 11 decimal places means that if the electron has any internal structure at all, it is hidden at energy scales so far beyond anything we can currently probe that it leaves no detectable fingerprint even at this extraordinary level of precision. Could electrons be composite? Could there be smaller objects, sometimes called preons, a generic name for hypothetical subelectron constituents proposed by various theorists starting in the 1970s? lurking at scales beyond our reach? Logically, the answer is yes. Physics is empirical, and we can only know what experiments tell us. History has repeatedly shown that objects believed to be fundamental turned out to have structure when probed at higher energies. Atoms were thought indivisible until Thomson found the electron. Nuclei were thought fundamental until Rutherford found the proton and neutron. Protons were thought fundamental until deep inelastic scattering at SLAC in the late 1960s revealed the quarks moving inside them. Each increase in collision energy peeled back another layer of structure, but the electron's case is different in a key way. The constraints from precision measurements, particularly the magnetic moment, are so tight that any preon model must produce predictions indistinguishable from a structureless point, particle to better than 1 part in 10 billion. Building a model of bound subparticles that satisfies this constraint while also explaining the electron's tiny mass, which is far smaller than the energies at which compositeness would be relevant, is extraordinarily difficult, bordering on technically impossible. Most physicists regard the electron as genuinely fundamental at all accessible scales, while acknowledging that absolute certainty is not something physics can offer. What is certain is that the electron's observable properties are described with extraordinary fidelity by the equations of QED and the Standard Model of particle physics, the theoretical framework that accounts for all known particles and forces except gravity. In the Standard Model, the electron is classified as a lepton, one of 6, the lightest and most familiar, the others being the muon and tau and their associated neutrinos. The muon is essentially an electron that weighs about 200 times more. The tau is heavier still by another factor of 17. These 3 generations, electron, muon, tau, are for all observable purposes identical, except in mass. They have the same charge, the same spin, the same types of interactions. Nature appears to have photocopied the electron recipe twice at increasing mass scales, for reasons that remain entirely unknown. When the muon was discovered in the late 1930s, the physicist Isidore Rabi reportedly expressed the bewilderment of the entire physics community in 4 words. Who ordered that? The muon had not been predicted by any theory. Nobody had suggested it. Nobody had a reason to expect it. It arrived like an uninvited guest who turns out to be identical to a guest you already know, just slightly heavier, and refuses to explain their presence. Nearly a century later, the 3-generation structure of the Standard Model remains one of its deepest unexplained features. The mathematics accommodates it. It does not explain it. The Standard Model also cannot tell you why the electron has the specific mass it has. The Higgs mechanism, confirmed in 2012 with the discovery of the Higgs boson at CERN's Large Hadron Collider, the culmination of nearly 50 years of theoretical prediction and experimental search, explains how the electron acquires mass in the first place. The Higgs field permeates all of space with a non-zero value, and when fundamental particles interact with it, they acquire mass proportional to the strength of their coupling to the field. The electron couples weakly, so it is light. The top quark, the heaviest known fundamental particle, couples strongly, making it roughly 300,000 times heavier than the electron. But why the electron-Higgs coupling has the particular value it has, why the electron is as light as it is rather than twice as light or twice as heavy, is simply not explained. It is a parameter of the theory. Measured, inserted, used, not derived. This is one of the profound open wounds in fundamental physics. The Standard Model contains roughly 19 free parameters, numbers that must be fed into the theory from experiment rather than being predicted from first principles. The electron's mass is one of them. The electron's charge is related to another, the electromagnetic coupling constant. A truly complete theory of nature would derive these values from something deeper, would explain rather than merely describe. We do not yet have such a theory. And there is a stranger question still, beneath even the question of why the electron has the mass it does. Why does the electron exist at all? Why is there an electron field in the universe? The Standard Model takes the content of the universe as a given. Here are the fields, here are their interactions. Go compute. It does not explain why these particular fields exist. Why the universe chose this set of quantum fields rather than some other set or no fields at all. The deepest question, why is there something rather than nothing, and why is that something this, falls outside the Standard Model's jurisdiction and remains unanswered by any current physics. But consider how far we have come from the crisis of the early 20th century. We started with a catastrophic failure. The classical picture of the atom predicted its own immediate collapse. Every atom in the universe should have dissolved in a trillionth of a second. Nothing solid should exist. We had to throw away 2 centuries of classical certainty and rebuild from the ground up. What replaced it is something both stranger and more beautiful than anyone could have anticipated. The electron is not a particle in the classical sense. It is not a tiny physical object following a path through space. It is a quantum entity described by a wave function, a probability cloud, a fundamental excitation of a field that fills the universe. Its position is not defined until you measure it. Its energy is not continuous but quantized, taking only specific allowed values determined by the mathematics of the Schrödinger equation. And the lowest of those values, the ground state, has a finite, non-zero energy corresponding to a non-zero spatial extent. The electron cannot fall into the nucleus because doing so would require the electron to occupy a state with lower energy than the ground state allows, and such a state does not exist. The universe ran out of lows. The uncertainty principle provides the physical mechanism. Confinement increases kinetic energy. The ground state is where the competing demands of electrical attraction and quantum kinetic energy reach their minimum combined value. The atom's stability is not the result of some lucky balance of forces that might one day tip the wrong way. It is the result of the mathematical structure of quantum mechanics having a floor, an absolute lowest point below which no quantum state exists. The stability is permanent, absolute, built into the laws of physics at the deepest level accessible to us. And this stability is the reason the world exists. Think about what follows from it. Atoms are stable, which means molecules can form, 2 or more atoms sharing or transferring electrons, in arrangements that lower their combined energy, held together by the same quantum mechanical rules that keep each atom intact. Molecules can form complex structures, which means chemistry exists. Chemistry exists, which means the rich variety of materials composing the observable world is possible. Metals and minerals, gases and liquids, polymers and crystals, biological macromolecules of extraordinary complexity. Biological macromolecules can encode and execute self-replicating processes, which means life exists. Life can develop nervous systems capable of modeling the world and generating questions about their own nature, which means minds exist. Minds can direct the construction of experimental apparatus and develop mathematical frameworks powerful enough to peer into the quantum structure of the atom and discover the very rules responsible for their own existence. Every step in this chain depends on the step before it, and the first step, the stability of the atom, depends entirely on the wave nature of the electron and the uncertainty principle forbidding its collapse. The universe's complexity, its richness, its capacity to produce you reading these words with the specific feeling of understanding something deep, all of it traces back to the floor that quantum mechanics place beneath the electron's energy, preventing its descent. The solidity of the table beneath your hands is not a property of the table's atoms being close together or touching each other. The atoms are mostly space. The solidity comes from the electron clouds of those atoms resisting compression through a combination of electromagnetic repulsion and a second quantum mechanical effect, the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. This principle states that no 2 fermions, and electrons are fermions, particles with half-integer spin, can occupy the same quantum state simultaneously. No 2 electrons anywhere can have identical values for all their quantum numbers at the same time. This is not a consequence of electrons repelling each other electromagnetically. It is deeper than that. It is a consequence of the mathematical symmetry of quantum mechanical wave functions for identical particles. When you write a wave function for 2 electrons, the mathematics requires it to be antisymmetric. If you swap the 2 electrons, the wave function must flip its sign. If both electrons were in the same quantum state, swapping them would leave the wave function unchanged, which means it must simultaneously equal minus itself, which is only possible if it equals zero probability. The configuration is physically forbidden, not by any force, but by the structure of mathematics itself. This exclusion is what gives ordinary matter its volume. When you press your hand against a surface, the electron clouds of your skin atoms and the surface atoms begin to overlap. But the Pauli exclusion principle prevents those electrons from all settling into the same lowest energy states. They must occupy higher and higher states as the overlap increases, and higher states require more spatial room. The resistance you feel, the firmness of a table, the pressure of a wall, is the quantum mechanical universe preventing the occupation of already claimed energy states. The solid world is built from the refusal of electrons to share. The Pauli exclusion principle also holds up stars. When a star exhausts its nuclear fuel and collapses under its own gravity. What halts the collapse for stars of modest mass, creating a white dwarf, is the electron degeneracy pressure generated by the exclusion principle. The electrons in the collapsing stellar material are being squeezed together, forced into a smaller and smaller volume. But the exclusion principle prevents them from all falling to the lowest energy state. They must pile into progressively higher states, and this piling generates a pressure, not from thermal motion, not from any classical force, but from the quantum mechanical prohibition on identical quantum states, that pushes back against gravity and holds the star at a finite size. Without quantum mechanics, white dwarfs would not exist. They would collapse to black holes. The night sky would look different, and the universe would have a different structure of stellar remnants threading through it. In neutron stars, denser still, the end state of more massive collapsing stars. It is the Pauli exclusion principle acting on neutrons that resists further collapse. Neutrons, like electrons, are fermions. They obey the same anti-symmetry rule. Pack them tightly enough, and they too resist being forced into already occupied states, generating neutron degeneracy pressure that supports the star against gravity at nuclear densities, with a teaspoon of neutron star material massing billions of tons. The smallest and densest stable objects in the known universe owe their existence to the same quantum principle that makes your hand solid. We live inside a universe made coherent by quantum mechanical rules we are still in the process of fully understanding. The electron, for all that we know about it, and what we know is staggering in its precision and depth, remains in some respects mysterious. Its mass, its charge, the reason there are 3 generations of leptons, the relationship between its properties and the properties of the quarks that make up protons and neutrons. These are open questions. The Standard Model describes the electron's behavior with extraordinary accuracy and says almost nothing about why the electron is the way it is. A deeper theory, whether some form of string theory or something not yet conceived, might one day answer these questions, deriving the electron's mass and charge from some more fundamental geometrical or algebraic structure, explaining the 3-generation pattern, revealing whether the electron is truly elementary or whether there are still smaller objects waiting to be found at energies beyond current reach. But what is certain now, from a century of quantum mechanics built on a foundation of theory and experiment, intertwined in continuous dialogue, is this. The electron does not fall into the nucleus because quantum mechanics forbids states below the ground state. The ground state exists because the electron's wave nature, combined with the uncertainty principle, creates a minimum energy configuration at a finite distance from the nucleus. That minimum exists because the kinetic energy cost of confinement competes with the potential energy benefit of proximity, and the competition resolves at a specific finite radius. The atom is stable not because of any force propping the electron up, not because of any orbit balancing speed against gravity, but because the quantum structure of reality has an absolute floor, and the electron is already standing on it. This is not a metaphor or an approximation. This is the literal reason that matter exists in its present stable form, the reason that atoms survive, the reason that chemistry works, the reason that biological complexity is possible, the reason that any of this, stars, planets, rivers, fossils, cities, words, thoughts, came to exist at all. The floor of the quantum energy ladder is the foundation of the world. And the electron, this tiny, fundamental, structureless ripple in a quantum field that fills the universe, is the entity that stands on that foundation, holding everything up, making every atom of every substance in existence stable against the electrical catastrophe that classical physics predicted with total confidence and quantum mechanics quietly, completely, permanently prevented. When physicists first glimpsed the quantum world in those extraordinary years between 1900 and 1930, none of them, not Planck, not Einstein, not Bohr, not Schrödinger, not Heisenberg, fully understood where the mathematics was leading. They built the framework piece by piece, often in mutual disagreement about what it meant, arguing fiercely about interpretation, while the equations accumulated remarkable agreement with experiment. What emerged from that process was not just a better description of the atom, it was a completely new understanding of the structure of reality. Probabilistic, quantized, wave-like, non-local in ways that still provoke debate, and underneath all the strangeness, quietly and absolutely ensuring that the atoms composing the universe remain intact. There is something philosophically extraordinary about this situation. The universe is set up in such a way that its basic constituents, electrons, quarks, the particles that compose all matter, obey rules that prevent catastrophic collapse. Those rules were not designed by anyone and arise from the mathematics of quantum field theory in a way that we can describe with equations of breathtaking precision, but cannot ultimately explain in terms of something simpler. The rules are the rules. They apply everywhere, always, without exception. And one of their primary consequences is that you exist, that matter is stable, that atoms endure, that the long chain of chemical and biological complexity that produced you and your capacity to wonder about electrons could unfold over cosmic time. The question we began with, why doesn't the electron fall into the nucleus, turns out to be not a narrow technical puzzle, but a window into the deepest workings of the universe. To answer it fully, you have to understand electromagnetic theory and why it fails at atomic scales. You have to grasp quantum mechanics and the wave nature of matter. You have to encounter the uncertainty principle and recognize its role as a structural feature of reality rather than an epistemic limitation. You have to learn about quantum field theory and the nature of the electron as a field excitation rather than a classical particle. You have to wrestle with the Pauli exclusion principle and see how it shapes not just atoms, but stars. You have to travel from the experiments of the early 20th century to the most precisely tested predictions in the history of science. You have to hold in mind simultaneously that the electron has no known size, no known internal structure, and no explanation for its specific mass and charge, while also being the most carefully characterized object in physics. But before we reach that final reckoning, there is more territory to cover. Territory that illuminates the electron from angles that neither classical intuition nor even early quantum mechanics could have prepared us for. Because the quantum world does not stop at discrete energy levels and probability clouds. It goes deeper, it becomes stranger. And the strangeness, as always, is not a defect or a mystery to be embarrassed about. It is the landscape of how things actually are. Consider what happens when you look more carefully at the electron inside the atom, not just at where it is most likely to be found, but at the shapes that its probability cloud can take in the excited states above the ground state. In the ground state, the wave function is spherically symmetric. The probability cloud is a perfect fuzzy sphere centered on the nucleus, the same in every direction. But the second energy level admits wave functions of a different character entirely. Some of them have two lobes pointing in opposite directions, like a dumbbell oriented in space, with a flat plane of zero probability cutting between them. Others form rings. Still, others combine these features. The third energy level brings even more elaborate geometries, four-lobed arrangements, toroidal shapes, patterns of nodes that carve the probability cloud into elaborate three-dimensional sculptures. These shapes are not decorative. They are the orbitals of chemistry, the structures that determine how atoms bond to one another, how molecules acquire their three-dimensional form, how biological macromolecules fold into shapes that allow them to perform the specific biochemical functions on which life depends. The shape of a water molecule, the angle between its two hydrogen atoms, roughly 104 degrees, is a direct consequence of the shapes of oxygen's wave functions in the bonding state. The double helix of DNA is possible because the wave functions of carbon, nitrogen, oxygen, and phosphorus electrons adopt specific geometries that allow the molecular components to fit together in precisely the right way. Chemistry, at its most fundamental level, is applied quantum mechanics. Every bond, every reaction, every transition from one molecular form to another is an expression of electrons moving between allowed quantum states. The quantum numbers that label these states are not arbitrary labels chosen for bookkeeping convenience. They are the natural variables that emerge from the mathematics of the Schrödinger equation applied to the spherically symmetric potential of the nucleus. The principal quantum number specifies the energy level and can take any positive whole number value, 1, 2, 3, and so on, upward. The angular momentum quantum number specifies the shape of the wave function, whether it is spherical, dumbbell-like, four-lobed, or more complex, and can range from 0 to 1 less than the principal quantum number. The magnetic quantum number specifies the orientation of the shape in space, how it is pointing relative to an external reference direction, and takes integer values between the negative and positive values of the angular momentum quantum number. And the spin quantum number specifies whether the electron's intrinsic angular momentum is aligned parallel or antiparallel to any reference axis, taking only 2 values, up or down. The Pauli exclusion principle says no 2 electrons can share the same values of all 4 quantum numbers simultaneously. This is what builds the periodic table. The first energy level has only one possible wave function shape, spherical, and holds at most 2 electrons, 1 spin up and 1 spin down. The second energy level has 4 possible wave function shapes and holds at most 8 electrons. The third level has 9 shapes and holds up to 18. As you add electrons to an atom, as you move from hydrogen with 1 electron to helium with 2 to lithium with 3 and beyond, each new electron must occupy an available quantum state that no other electron in that atom already occupies. The pattern of filling determines the chemical properties of each element, which is why elements separated by the same periodicity in the table share similar properties. They have similar outer shell electronic configurations, and it is the outermost electrons that engage in chemical bonding. The periodic table is not an empirical list of facts discovered by chemists through centuries of experiment and memorized by students under duress. It is a consequence of quantum mechanics. Its structure, the periods of length 2, 8, 18, reflects the number of available quantum states at each energy level. The chemical similarities between elements in the same column are not coincidences or arbitrary associations. They are geometric necessities arising from the mathematics of wave functions in a central potential. The entire chemistry of the known universe is a readout of quantum number arithmetic. The same quantum mechanics that explains atomic stability also explains the material properties of matter and bulk. Why is iron magnetic? Because the wave functions of iron's electrons in the partially filled third shell have an intrinsic preference, due to a quantum mechanical principle called Hund's rule, to align their spins parallel to each other before any pairing begins. This parallel alignment of many electron spins in the atoms of iron, combined with the quantum exchange interaction that correlates the behavior of electrons in neighboring atoms, produces the macroscopic magnetic ordering that makes iron a ferromagnet. The magnetism of iron is quantum mechanics operating at the scale of bulk material through trillions of correlated electron states. Why are metals conductive while insulators are not? In a metal, the outermost electrons are in quantum states that extend across the entire bulk of the material, essentially free to move throughout the sample, responding to an applied electric field by drifting collectively and constituting an electric current. In an insulator, the outermost electrons are in localized states, trapped around individual atoms or in bonds between atoms, unable to move freely in response to an applied field. The distinction between conductors and insulators is a distinction between quantum states that are delocalized across a macroscopic sample and quantum states that are not. Semiconductors, the materials at the heart of every microprocessor and solar cell, sit between these extremes with energy structures that allow conduction to be switched on and off by adding impurities or applying voltages. The entire technology of the modern world, from smartphones to medical imaging to satellite communication, runs on the quantum mechanics of electrons and solids. Superconductivity, the phenomenon where certain materials, cooled below a critical temperature, carry electric current with absolutely zero resistance, is even more dramatically quantum. In a superconductor, pairs of electrons form a correlated quantum state that extends across the entire macroscopic sample. These pairs, called Cooper pairs, after the physicist Leon Cooper, who explained their formation in 1956, condense into a collective quantum state, a macroscopic quantum phenomenon, where the pair wave function has a definite phase across distances of centimeters or even meters. The electric current in a superconductor is not individual electrons diffusing through a lattice, but a single quantum state carrying charge, immune to the scattering that causes resistance in ordinary conductors because any scattering event would have to disturb the entire correlated pair state simultaneously, which costs far too much energy. Superconductivity is quantum mechanics visible at human scales. The laser, one of the most transformative technologies ever developed, is also a quantum phenomenon at its core. A laser works by stimulating a population of excited electrons to return to their ground state in a coordinated fashion, emitting photons that are all in the same quantum state, the same frequency, phase, and direction. This coherent emission is not possible in classical physics. It arises from the quantum statistical behavior of photons, which, unlike electrons, are not subject to the Pauli exclusion principle. Photons are bosons, particles with integer spin, and bosons follow different quantum statistical rules. They actively prefer to occupy the same quantum state. Many photons in the same state is more probable, not less. The laser exploits this preference to build a bright, coherent, highly directed beam of light from the quantum transitions of electrons between energy levels. Every time a surgeon uses a laser scalpel, every time a barcode reader scans a label, every time a fiber optic cable carries a phone call around the world, the quantum mechanics of the electron's energy levels is at work. And then there is quantum tunneling, a phenomenon with no classical analog, a direct consequence of the wave nature of quantum particles, responsible for nuclear fusion in the sun, for the operation of the scanning tunneling microscope, for the alpha decay of radioactive nuclei, and for the reliability of the semiconductor transistors in every computer chip ever manufactured. In classical physics, a particle that encounters a barrier higher than its kinetic energy simply cannot cross. It bounces back every time, without exception. But in quantum mechanics, the wave function does not abruptly become zero at the boundary of the barrier. It decays exponentially inside the barrier, falling to smaller and smaller values. But if the barrier is thin enough, there is a non-zero probability of finding the particle on the far side. The particle has passed through the classically impenetrable barrier, not by going over it or around it, but by having a wave function that penetrates it. This is quantum tunneling. The sun burns because of tunneling. The fusion reactions at the solar core require protons to come close enough together for the strong nuclear force to take hold. But electrostatic repulsion between the protons creates an energy barrier far higher than the thermal energies available inside the sun. Classical physics says solar fusion should be essentially impossible at the sun's core temperature. But the protons are quantum particles. Their wave functions overlap even when the classically calculated energy barrier says they should not. There is a small probability of tunneling through the barrier on each close approach, and with enough protons attempting this transition every second, roughly 10 to the 38th collisions per second, the aggregate tunneling rate sustains the nuclear fire that has been warming Earth for 4.5 billion years. The sun's light is a quantum mechanical phenomenon. Without tunneling, without the wave nature of matter, the sun would be dark and the Earth would be frozen. Tunneling also lies at the heart of radioactive decay. When a nucleus emits an alpha particle, 2 protons and 2 neutrons moving together, the alpha particle does not have enough energy, in classical terms, to escape the attractive strong nuclear force binding it to the remaining nucleus. But the alpha particle, like all quantum particles, has a wave function that extends beyond the barrier. There is a finite probability at each moment that the alpha particle is found outside the nucleus, having tunneled through the barrier. The half-life of the radioactive nucleus, the time it takes for half a sample to decay, is directly related to the tunneling probability. Nuclei with higher barriers or thicker barriers tunnel less frequently and have longer half-lives. Nuclei with lower, thinner barriers tunnel more often and decay quickly. The mathematics of quantum tunneling predicts radioactive half-lives that span more than 40 orders of magnitude, from fractions of a second to billions of years, and the predictions match experimental measurements across this entire range. Every atom of uranium in the Earth's crust has a half-life of 4.5 billion years, because the alpha particle tunneling probability through the strong nuclear barrier is extremely small, so small that only one nucleus out of roughly 10 to the 38th tunnels in any given second. That tiny tunneling probability, combined with the roughly 10 to the 50th uranium atoms that have existed since Earth formed, produces the observed radioactivity that has been gently warming the Earth's interior since its formation, driving plate tectonics, volcanic activity, and the geological cycles that have recycled carbon and nutrients through the biosphere for billions of years. The heat that moves continents and builds mountains is powered by quantum tunneling. The breadth of quantum mechanics' reach is staggering. It is not a theory about small things that happens to be relevant only when you go looking for small things in laboratories. It is the framework governing the behavior of all matter and energy at the most fundamental level, and its consequences scale upward through chemistry, materials, science, biology, geology, astrophysics, and cosmology, touching essentially every phenomenon in the natural world. The stability of the atom is where quantum mechanics is most dramatically necessary, where the classical alternative is most obviously catastrophic. But it is far from where quantum mechanics stops mattering. Come back then to the electron. Having understood how far its quantum nature reaches, how many features of the world depend on it, let us look once more at what physics currently knows and does not know about this fundamental entity. The Standard Model, as presently formulated, describes 3 generations of matter particles, quarks and leptons, each appearing in 3 versions that are structurally identical but differ enormously in mass. The first generation, up and down quarks, the electron, and its associated neutrino, forms all stable ordinary matter. The proton is 2 up quarks and 1 down quark. The neutron is 2 down quarks and 1 up quark. Hydrogen is 1 proton and 1 electron. Everything else is combinations of these. The second generation, charm and strange quarks, the muon and its neutrino, is heavier and unstable, produced in high-energy collisions and quickly decaying back to first-generation particles. The third, top and bottom quarks, the tau and its neutrino, is heavier still, even more transient. Nobody predicted this structure before it was discovered. Nobody predicted the muon. Nobody predicted the tau. Each new generation arrived as a surprise, forcing theorists to expand their frameworks. The Standard Model has been modified to accommodate the 3 generations, and the mathematics works seamlessly. The theory is consistent with 3 generations and fits all available data, but it offers no explanation for why 3 and not 2 or 4 or 17. There is no derivation within the Standard Model of why the pattern repeats exactly 3 times. It is simply observed to do so and accommodated. This is one of the places where physicists most acutely feel the incompleteness of the current theoretical situation. The Standard Model is spectacularly successful as a predictive framework. Its predictions for particle interactions have been confirmed to extraordinary precision across decades of increasingly powerful experiments. But it is explicitly not a complete explanation of reality. It is a description, not an explanation. It tells you what particles exist and how they interact, but not why they exist, why they have the properties they do, or what principle determines the overall structure of the theory. The charges of particles provide another example of unexplained numerical coincidence that physicists find deeply unsatisfying. The electron's charge is -1 in natural units. The proton's charge is +1. Exactly 1 to all measurable precision, with no discrepancy detected at any level of experimental sensitivity. The proton is built from 3 quarks, 2 with charge positive 2/3 and 1 with charge negative 1/3. These fractions sum to exactly 1. The match between the electron's charge magnitude and the proton's charge magnitude is therefore precise, and yet the electron is a lepton, a fundamental particle of one type, while the quarks are an entirely different class of particle with fractional charges, bound by a different force, described by a different field theory. In the Standard Model, there is no obvious reason these two entirely different types of particles should have charges that cancel so perfectly. The consequence of this cancellation is enormously important. Atoms are electrically neutral. A hydrogen atom with 1 proton and 1 electron has exactly 0 net charge. Not almost 0, but precisely 0, because the proton's charge is precisely cancelled by the electrons. This charge neutrality of atoms is what allows the large-scale universe to be electrically neutral, why ordinary matter does not spontaneously fly apart under its own electrical repulsion, why gravity can dominate at macroscopic scales even though it is by far the weakest fundamental force. If the electron's charge were different from the proton's by even 1 part in a billion, the resulting net charge on each atom would create electrical forces that would overwhelm gravity at astronomical scales, preventing galaxies from forming. The universe would be an electrically convulsing plasma of bare charges, with no atoms, no chemistry, no stars, no planets, no life. Grand unified theories, speculative extensions of the Standard Model that attempt to merge the electromagnetic, weak nuclear, and strong nuclear forces into a single unified interaction at very high energies, can explain why the electron and proton charges are exactly equal in magnitude. In these theories, quarks and leptons are different manifestations of the same, more fundamental set of fields, connected by a larger symmetry. The charge quantization that seems coincidental in the Standard Model becomes a mathematical necessity in the unified theory. At sufficiently high energies, far beyond what any current or foreseeable accelerator can reach, the 3 forces would merge into one, and the separate descriptions of quarks and leptons as different types of particles would dissolve into a unified picture. The most dramatic prediction of grand unified theories is the decay of the proton. If quarks and leptons are ultimately the same thing at high energy, then there should be processes, extremely rare, mediated by extraordinarily massive force carrier particles, that convert quarks into leptons. A proton could emit such a particle, converting one of its quarks into a lepton, producing a meson and a positron. The predicted rate of this process, in most grand unified theories, corresponds to a proton lifetime of roughly 10 to the 34th years or more, enormously longer than the current age of the universe. Detecting this process requires watching enormous quantities of protons for long periods. Facilities like the Super Kamiokande detector in Japan, a tank containing 50,000 tons of ultra-pure water surrounded by light detectors, have been doing exactly this for decades. The water provides a target of roughly 10 to the 33 protons to watch. So far, no proton decay event has been definitively observed. This rules out the simplest grand unified theories, but leaves more sophisticated versions intact. The running of coupling constants is another window into possible unification. At low energies, the energies accessible to us in everyday experience and in most particle physics experiments, the 3 non-gravitational forces have very different strengths. The strong nuclear force is about 100 times stronger than the electromagnetic force at the nuclear scale, and the weak force falls between them. But the strengths of these forces are not fixed. They change with energy scale. As we discussed when considering the electron's charge, the coupling constants run. When physicists extrapolate the measured running of all 3 coupling constants to higher and higher energies, the 3 values appear to converge toward one another at an energy of roughly 10 to the 15th to 10 to the 16 giga-electron volts. The expected scale of grand unification. The convergence is not exact in the minimal Standard Model, but becomes more precise when supersymmetry, a theoretical extension that pairs each known particle with a heavier partner, is included. Supersymmetry has its own attraction as a possible explanation for why the Higgs boson mass is as light as it is, rather than being pulled to much higher energies by quantum corrections. The Higgs mass, unlike the gauge boson masses, is not protected by the symmetries of the Standard Model and receives large quantum corrections from the virtual particles whose existence QED tells us surrounds every fundamental particle interaction. Without some cancellation mechanism, these corrections would drive the Higgs mass to the much higher scales associated with grand unification, or the Planck scale, 16 orders of magnitude above the observed mass. Supersymmetry provides automatic cancellation. The quantum corrections from ordinary particles are precisely cancelled by equal and opposite corrections from the supersymmetric partners. The result is a natural Higgs mass at the electroweak scale where it is observed. Supersymmetry has been searched for extensively at the Large Hadron Collider since it began operating at full energy in 2015. No supersymmetric particles have been found. This does not rule out supersymmetry. The partner particles might be heavier than the LHC can produce, or they might decay in ways that make them harder to detect. But it has progressively constrained the simplest and most attractive versions of the theory. The theoretical landscape for beyond Standard Model physics remains rich in proposals and sparse in confirmation. This is the frontier where physics currently stands. With a theory, the Standard Model, of extraordinary predictive power and acknowledged incompleteness, surrounded by a proliferation of proposed extensions that have so far not found experimental confirmation. The electron sits at the center of this situation. It is the best studied fundamental particle, the one whose properties are most precisely measured, the one whose interactions are described with the most precise tested theory. And yet its deepest properties, why it has the mass it has, why it exists as one of three structurally identical leptons, why its charge exactly cancels the protons, remain without fundamental explanation. This is not a failure of physics. It is a frontier. Every era of physics has had its frontiers, places where the current best theory runs into questions it cannot answer, pointing toward the existence of deeper structure. In each case, the frontier eventually resolved into a new theory that answered the old questions while opening new ones. The electron's mysteries are not evidence that something has gone wrong in physics. They are evidence that something interesting remains to be discovered, that the story of matter and energy, of fields and forces, has chapters not yet written. And yet, with all this incompleteness acknowledged, something must be said about what has already been achieved, about what we do know, about the distance traveled from the catastrophic failure of classical physics before a hot, crowded room of anxious early 20th century physicists to the quantum field theoretic framework that describes the electron's behavior to 11 decimal places. That journey was one of the most demanding and disorienting in intellectual history, requiring the abandonment of deeply held intuitions about what it means for something to have a position, what it means for a property to exist before it is measured, what reality is doing between observations. The classical physicist believed that the world had a definite state at every moment, whether or not anyone was looking. Planets moved along their trajectories through the solar system, regardless of whether any astronomer was watching. The electron, in the Thomson and Rutherford models, was somewhere definite at every moment, moving through space in a definite way, following the electromagnetic forces acting on it. The task of physics was to calculate that trajectory and predict where the electron would be at any future time. Quantum mechanics says this picture is not just imprecise, but wrong in principle. The electron does not have a definite position between measurements. It does not follow a trajectory. The wave function does not describe our ignorance of where the electron is. It describes the electron's actual physical state, which is one of genuine indeterminacy, spread across space, existing simultaneously in multiple configurations, choosing a definite value only when forced to by the act of measurement. And this choice, when it happens, is genuinely random, not pseudo-random, not determined by hidden information we do not have access to, but irreducibly, fundamentally random, in a way that the universe itself does not know the outcome of in advance. Einstein famously struggled with this interpretation for the last 30 years of his life, insisting that quantum mechanics must be incomplete, that there must be additional variables, hidden variables, whose values determine outcomes that appear random only because we cannot see them. His 1935 paper with Boris Podolsky and Nathan Rosen described what seemed to be a paradox. Quantum mechanics predicted that two particles, once they had interacted, would remain correlated in their properties instantaneously across any distance, so that measuring one would immediately determine the outcome of measuring the other. Einstein felt this was impossible without some pre-existing agreement built into the particles at the time they interacted, some hidden variable that carried the correlation. To require faster-than-light influence to explain the correlation seemed to him a violation of the locality principle he considered essential to physics. John Bell, working in 1964 at CERN, translated this philosophical disagreement into a mathematical prediction. If hidden variables existed and the correlations were pre-established, the correlations between measurements on separated particles could not exceed certain limits. Mathematical inequalities now known as Bell inequalities. If quantum mechanics was correct, the correlations would violate these inequalities, exceeding the maximum values that any local hidden variable theory could produce. The two possibilities made different, testable predictions. Experiment could decide. Beginning in the 1970s with pioneering work by John Clauser, Stuart Friedman, and others, and continuing through increasingly refined experiments by Alain Aspect in the 1980s and many subsequent investigators up to the loophole free Bell tests of 2015 and beyond, experiments have repeatedly and decisively confirmed that nature violates Bell inequalities. The correlations between distant quantum particles are stronger than any local hidden variable theory allows. The correlations are real. They are not pre-established at the time of interaction by some hidden mechanism. They are, in whatever sense this can be said, non-local, present across space in a way that cannot be explained by any message or signal traveling between the particles after their separation. This does not allow faster-than-light communication. The quantum correlations cannot be exploited to send information, because the individual measurement outcomes are still random. But it does mean that the quantum world is genuinely non-local in a precise technical sense. The description of two entangled particles is irreducibly a description of the pair, not of two independent individuals. The whole is more than the sum of its parts in a way that has no classical equivalent. Einstein was wrong about hidden variables. Quantum mechanics is not incomplete in the way he feared. The universe is, at the most fundamental level, non-local. This non-locality, entanglement, is now being actively exploited in emerging quantum technologies. Quantum cryptography uses entangled photons to distribute encryption keys whose security is guaranteed by the laws of physics. Any eavesdropping disturbs the quantum state in detectable ways, making undetected interception impossible in principle. Quantum computing uses entangled quantum states to perform certain calculations, exponentially faster than any classical computer can. Not because the quantum computer is faster in the ordinary sense, but because quantum superposition allows it to explore many computational paths simultaneously, in a way that has no classical analog. The same quantum indeterminacy that once seemed like a source of philosophical anxiety is now a computational resource. All of this, the entanglement, the quantum computing, the cryptographic security, the precision measurements, the Pauli exclusion principle operating in white dwarfs, the tunneling sustaining the sun, flows from the same source, the quantum nature of matter, the wave function, and the Schrödinger equation, the uncertainty principle, the discrete energy levels, the ground state floor that holds the electron in place and holds the atom together and holds the world in existence. And at the end of all this, the answer is both simple and profound. The electron does not fall into the nucleus because there is no state below the ground state, because the ground state's existence is mandated by the mathematics of quantum mechanics applied to the Coulomb potential, because the uncertainty principle converts spatial confinement into kinetic energy in a way that sets a minimum distance and a minimum energy, because quantum fields permeating the universe give rise to localized excitations, electrons, whose properties are fixed by the field and whose behavior is governed by equations that have, baked into them, a lowest rung from which no further descent is possible. The floor is real, the electron is on it, matter survives, you exist, and somewhere in the quantum fields that fill the space around you right now, between your fingers and the device you are holding, in the air you are breathing, in the trillions of atoms of your own body, electrons are doing exactly what the equations say they do. not orbiting, not spiraling, not following any path, simply existing in the lowest available quantum state, in their probability clouds, in their standing wave patterns around their nuclei, in the configuration that the mathematics of the universe has designated as the bottom, the configuration below which reality offers nothing, stable, permanent, holding the world together with the most elegant and unexpected mechanism imaginable, the simple, absolute, mathematically mandated non-existence of anything lower.